This is my simplification of the economic evaluation on the cost effectiveness of a newborn screening program published in the Pediatrics Journal article in this week's required readings. We just configure the model as a cost effectiveness model as usual. Now in my other slides, much of what we've done in terms of sensitivity analysis on these evaluations has been deterministic sensitivity analysis. So deterministic sensitivity analysis is where, given a willingness to pay, there's still, given the willingness to pay and some input parameters, so in pediatric telemedicine we had the effectiveness and the number of people using it, so you define those variables and you define the willingness to pay, and you make a recommendation based on that. Now we're going to expand the scope of economic evaluations to include probabilistic sensitivity analysis. So in the beginning of the course, in the first few slide sets, what we did is we were just putting numbers into TreeAge. So the cost and the effectiveness are just numbers. They're just entirely determined. You set the willingness to pay, you do a rollback on the tree. Then the next thing we did is we started adding variables. So remember how in some of the earlier slides is instead of saying that cost is equal 5, we'd say cost is some function. So cost is some function, like the cost of an injection drug program was cost of the relative cost function of the relative risk of sharing needles in the community, and then the number of people who are injecting drugs, and that would determine whether or not you would build the injection sites to combat the injection drug epidemic. So we had just numbers, and then we had variables, and now you can see I'm entering distributions. So distributions are adding even more detail to the model. So we're going to say the cost of screening is distributed following a normal distribution. You can see some different shapes there. We just put normal, with a mean cost of $45,000 and a standard deviation of $100,000. So you could use different distributions, and in the readings, they'll write in the tables, in their data tables, what distributions they're using. So you use some distributions for cost, some distributions for qualities, and you can see gamma distributions are pretty common. And there's different types of distributions you could use. You only need one distribution to do the analysis I'm doing in the set of slides. So we just distributed cost, and then you just make the variable equal to the distribution. So now the cost of the screening program follows a normal distribution. So sometimes the screening programs are really costly, sometimes they're really inexpensive, sometimes they're really expensive. And then the average cost of the screening program we said was $45,000, and then it has some standard deviation. So the idea of these distributions and a probabilistic model is that we're making an economic evaluation model of some underlying population, and we just sample from that. So there's a whole bunch of screening programs you can implement out there in the population, and sometimes they're really expensive, sometimes they're really inexpensive. On average, they cost $45,000, and we could use this model to evaluate a sample from this underlying population. The population parameters unknown, so think back to analytics or biostatistics if you talk about sampling from some underlying population, right? Population sort of infinite sample size, and then we're just going to evaluate, a random, literally a random sample of that larger population. You can see the cost effectiveness analysis here. So now how it's solving the model with rollback is it's setting the distribution equal to its mean. So we said that cost was distributed with a mean of $45,000 and a standard deviation of $100,000. In this base case scenario here, TreeAge is just ignoring the distribution and just taking the average of it. So the solution that's going to give you in rollback is when cost is equal to $45,000 per quality. So screening's more cost effectiveness, screening is more cost effective compared to no screening, given a cost of $45,000, that's the mean of the distribution. You want to do the rollback, we analyze it in more detail, and now we could see the influence of that cost distribution on the probability that it's cost effective. So you can see here is the option is called Monte Carlo simulation. And so we're simulating a random sample of that population. How many samples? Well, the larger the samples, the better, and the more precise your estimates are. 1,000 is usually fine. So in general, if you're doing Monte Carlo simulation of some straightforward economic evaluation model, you could probably just start with 1,000 for the number of draws you take from the distribution. So now since we said that cost was distributed, it had a mean and a standard deviation earlier in the slides, now what we get is that the cost has a mean and a standard deviation, and then The effectiveness of screening and no screening also have means and standard deviations, and same with the net monetary benefits. So when you have at least one distribution and you do this probabilistic Monte Carlo simulation, evaluate a sample of the larger population, this does is the distributions and the probabilistic analysis unlock new graphs. I'll just show you one of those graphs for now to simplify it, and then we could do others in the other slides. So this is called an acceptability curve. Up until this point in the course, we've been setting a willingness to pay equal to $50,000. But in some of the readings, they also question that $50,000 threshold. Maybe it's more, maybe it's less. And I think Newman, in one of the first readings in the course, said that 50,000 is outdated. It should probably be 100,000 or 150,000. So what we could do with probabilistic analysis is evaluate the percent that the screening intervention is cost effective for different values of willingness to pay. So the higher you are on that y-axis, the greater probability that the program is cost effective. So at $50,000, that's the base case scenario. It's going to match the rollback. Screening's more cost effective. The red bar is above the blue bar. If willingness to pay is only $10,000 or $20,000 per quality, then you would not choose screening. You're not willing to pay enough to scale up that supply curve from no screening to screening. So to the left of $50,000, willingness to pay under $50,000, you'll still choose no screening. But then if you're willing to pay $50,000 or more, you will choose screening. If you're willing to pay enough, you choose screening. So you're recommending for each willingness to pay, you're going to recommend whatever option is on that is higher on the y-axis, has the higher probability of being cost effective.